We want to wrap up chapter 16 by just kind of talking about some of the contexts and some of the applications of these ideas of reaction spontaneity. And so being able to predict whether or not a chemical reaction is going to happen is really kind of the basis of chemistry. And being able to know that if I mix this reactants, in these ratios or whatever, I can expect to make some certain amount of product. And being able to get that from tabulated data is huge, and being able to relate that to equilibrium constants. So you could figure out amounts of products and amounts of reactants that'd be at equilibrium. That would inform solution, mixture properties and all that kind of stuff is really, really important and really fundamental to kind of doing chemistry. And for another really important aspect of breaking it down into delta G, where we can decompose it into kind of the enthalpy and entropy driven ideas, lets us make predictions about how we can control spontaneity. Whether or not we want a reaction to happen or don't, how should we kind of move the temperature? How can we inform and kind of control how chemistry happens? And it's actually the same results as like the previous ideas from Le Chatelier's principle, but it's a bit more quantitative. It's a bit more explicit. These numbers are what you want to get to, this temperature, this, these pressures. You can get all sorts of information like that to really kind of guide explicitly, not just, you can know, just like make it hot will work. But explicitly like how hot kind of stuff. We can also, looking at like delta G tabulated information. You may have noticed we did an example, NO2 and N2O4. Both of their delta G's of formation were positive. And so what that actually means is that forming those compounds is not spontaneous. And in fact, the opposite direction is spontaneous. So something with a positive delta G, like N2O4, like NO2, implies that those molecules are unstable and they will spontaneously fall apart into the elements. But the kinetics are relatively slow in the gas. So both those are gases. And basically that equilibrium we saw was like the equilibrium constant was like a 3. So you get a mixture of both the gases. N2O4 is clear or colorless, and NO2 is brown. And so based on the temperature, these are different mixtures at different temperatures. You can see there's a relative preference for basically more or less of the other. And so these are what these molecules would fall apart in the gas phase over a very long time. But it does mean they're highly, highly reactive. So NO2 molecules won't fall apart in the gas phase, but say you breathe it in, all of a sudden you're allowing it to react with, say, the molecules in your throat, and that's going to react really, really quickly. So NO2 is brown. That's where the brownish color of smog comes from. So the brown you're seeing in there is brown from NO2. This is the skyline of Los Angeles in 2016. Very kind of known for city known for its smog. Greater Houston is not immune to this. It's just harder to get at an elevation where you can see the brown in the sky. If we think about kind of lab-based chemistry, we can kind of come to ideas like the fact that different metals have different tendencies to react with acid. So sodium, if you put it in acid, like lights up on fire. Magnesium bubbles vigorously, iron a little bit, lead very little, and then copper, not at all. Copper doesn't react when you put it in acid, it just sits there. And so why not? Okay, well, one of the things that we can kind of use as a way to kind of jump off from this is we can say that because that doesn't happen, we know that it's not spontaneous. And we therefore know that delta G is positive. For all these other metals, in their reaction with acid, delta G would be negative. So we know there's some sort of inherent kind of relationship here, or something that's changing. And we would expect to say sodium's delta G is very negative, whereas lead, because it doesn't have that much of a reaction, its delta G is not that negative. So if we want to figure out why, we can decompose these delta G's into an enthalpy part and an entropy part. And so in all of these reactions, it's an acid reacting with a metal. So the part of the acid that's reacting is, say, the H plus part of the acid. It reacts with a metal, you produce hydrogen gas, and then the metal becomes a cation. So the delta S for all these different reactions is very, very similar because it's all basically, you can see like one solid reactant becoming like one gas reactant. So you get like a huge increase in delta S as a result of this, because you make gas. But the thing is, across these different reactions, they all have the same delta S, roughly. So that means the variability in the spontaneity can be explained by just the delta H trends. So something like magnesium, where the delta H of the reaction is very negative, means that the delta G is also going to be negative. And that's why this reaction happens. So if we want to look at which metals react with acid, we only need to look at enthalpy, and it's all about then the relative stability of these different ions. Magnesium as a cation isn't that unstable. Magnesium has a relatively low ionization energy. Copper, on the other hand, has a really high ionization energy. It is really hard to remove electrons from copper atoms because it's really stable to have a full set of electrons around a copper atom. You can form copper 2+, but you got to put in a lot of energy, and that's displayed or kind of demonstrated by the high endothermic nature of this reaction. And so that's why copper doesn't react. The reason is because copper solid, the reactant's pretty stable, especially relative to copper 2+ cations being dissolved in solution. We can also turn to looking at things like dissolution and whether or not things are soluble, whether or not salts we would expect to, say, fully dissolve in solution. And so whenever we're looking at dissolving, we're taking a solid, in this case solid salts, and turning them into dissolved ions. So for these two reactions in particular, we know that delta S is going to be positive. So these, this is definitely dissolution. Dissolving things is favored based on an entropy side of things, but also it's usually endothermic. We can see here for both sodium chloride, dissolving is endothermic, and for silver chloride, it's also endothermic. So dissolving tends to be an entropy-driven process. One of the things we can take away from that right away is entropy-driven processes happen more readily at higher temperatures. So if you want to dissolve something, turning up the temperature usually is a good idea. Not always, there are some kind of fringe cases, but for the most part, if you want to get more to dissolve, i.e. this process becomes more spontaneous, you always want to turn up the temperature. And so, but, that's kind of explains the trend that we see, but in terms of controlling solubility. But what about why is AgCl not soluble and NaCl is soluble? They're both endothermic, but the question comes in is how endothermic? We can see that the NaCl is not very endothermic. It's only plus 3.8, whereas silver chloride, that's plus 65.7. And so this dependence on this kind of variation in delta H comes entirely based on the idea of kind of the interactions, the chemical interactions you're breaking, namely ionic bonds in the solid crystal, and then the interactions you're forming, namely the positive or negative end of the water dipoles interacting with the ions. We call that hydration. And so you have these kind of breaking of the ionic bonds and forming of the hydration interactions. And so for ions that have weak ionic bonds and strong hydration interactions, or relatively stronger hydration interactions, you'll have basically a less endothermic process. So that's why group 1A cations are always soluble. Sodium forms, all ionic bonds are strong, but sodium's ionic bonds aren't too crazy strong. But importantly, sodium forms very strong hydration interactions. Chloride forms pretty strong hydration interactions, but sodium forms extremely strong hydration interactions. It interacts with water very, very well, and that's why it will dissolve out in solution very well, because that is, you're forming these really, really good hydration interactions. Silver doesn't really interact with water very well at all. It's very weak hydration interactions. It actually has to do with that being a really big cation. Big things tend to not interact very well with water. And so these really, silver just doesn't form very strong hydration interactions. So you really just have a big cost of breaking the ionic bonds. And that's why silver tends to not be soluble. Lead tends to not be soluble. These really big cations that have strong interactions of ionic bonds, very weak hydration interactions. We can start to understand these trends that we have observed previously and make predictions kind of moving forward, or kind of understand concepts to make other predictions and apply these theories. That is it for chapter 16, going back to spontaneous processes, entropy, delta S with the second law of thermodynamics, and then delta G Gibbs free energy is kind of the main punchline or the main kind of point of chapter 6. So defining entropy and then using that
to kind of look at Gibbs free energy and characterize spontaneity of chemical reactions is really our big focus. All right, 3 questions on participation 327. You want to find all 3 of those questions, get them answered, and get those answers submitted over on Blackboard by Friday night. Week 10 homework due Saturday, covers all of chapter 16, acid-base titration post-lab due Sunday, blast from chapter 14 passed. That's it for me. The participation answers go live Friday night. Otherwise, have a good weekend. I will see you next week, week 11, continuing on. Moving into we'll do chapter 17 next. I'll see you there. Bye.